Hello and welcome. How are you doing? How's the class going? Are you feeling confident in proofs? Hopefully, after the long proofs project. Now we're switching gears. We'll still do some proofs, but we're going to start talking about number theory. And we're going to be studying integers and their properties. You should have a pretty good idea of what number theory is, and you should have watched most of the lectures and completed most of the work here in this first folder for Intro to Number Theory. I'm going to pick up on some stuff from the end of this section talking about the extended Euclidean algorithm. So I'm going to go into a little bit more detail because that can be kind of a tricky process at first. And I'm going to go through a few examples completing it by hand. And I just got an email. When I say by hand, what I mean is for you to show all your work and all your steps in this process versus automating the process with the Excel spreadsheet that I'm going to show you later, or plugging it into an online calculator. So I want to see all of your calculations. It doesn't matter if you type it or write it out. If you do want to write it out, because that can be a little bit easier time-wise, and you have a smartphone, you can always take a picture with an app like DocScan, or try to take a picture with your camera, and that might work to suffice as a scan. But mostly I just mean show all your steps, all your details, so that we are good. All right, so I'm going to start by, like I said, doing some examples of the extended Euclidean algorithm. After that, I want you to go through and complete this quiz, which is in the second folder here for Intro to Number Theory. So I want you to do some more practice. We're actually going to work through a couple of those, so you'll be able just to copy down basically the work that we did. But if you don't watch this video, you'll have to do it all. So I just want to show, I want you to show all your work on how you obtain that solution. So let's get started with an example here. So let's try to figure out the GCD of 16 and 17. And you should be familiar with what I mean by GCD. If you're not, then you need to go back and review the lectures and materials from the previous posts. So our goal here is to take the GCD of 16 and 17, whatever that might be, and write it as a linear combination of these inputs 16 and 17. And what I mean by a linear combination, let's see. Let me see if I can figure out, actually I might be able to figure out this linear combination without doing all this work. Well, maybe not. So if I do if I take 17 times 1, which is an integer, so as long as those coefficients are integers, I've written a linear combination. So negative 1, well, we're wanting it to be integers, at least in this case. Negative 1 times 16 plus 1 times 17 is 1. And so actually this is going to be the linear combination that we obtain, hopefully, if we do all the steps right. So usually when we get into bigger numbers, this linear combination could be a lot trickier to see. So on this one, maybe it's not too crazy to see, but I'm going to work through the Euclidean algorithm, which allows me to find that. So first I'm going to work through the Euclidean algorithm, and that will give me the GCD. So that last non-zero remainder, that will give me the GCD. So that'll help me find the GCD. So that's going to be my first step. And then I'm going to start with the extended Euclidean algorithm. And what the extended Euclidean algorithm gets us is this linear combination that I was talking about in the beginning here. So to do this process, the first thing that you do is solve for all the remainders. So you're just going to use what you did in the Euclidean algorithm and kind of manipulate those equations and do a bunch of substitutions. Solve for remainders, and you do substitution and simplification, right? Really, substitution, and simplification of the expression. So you're going to be combining like terms in a way that allows you to eventually end up with 16 as 17, as kind of think of them like variables when you're going through this. So every time you say think of a 16 and a 17, you can think about like x or y. So that way you're just manipulating those coefficients and leaving those alone. Okay, and it's kind of a weird process to get used to, but hopefully you've at least seen a couple examples by now and you've tried a couple examples, so this won't be too crazy to see. All right, so to get started here, I'm going to just start a new page here. So I'm going to talk about 16 and 17. So with the Euclidean algorithm, I'm always going to start with the bigger number. And again, this Euclidean algorithm is going to help me to find the GCD of 16 and 17. And hopefully you can reason through and see, well, 17 is prime. The only factors of 16 are 1, 2, let's see, factors of 16 are 1, 2, let's see, 3, no, 4, yes, 5, no, 6, no, 8, 7, no, 9, 10, 11, 12, 13, 14, 15, 16. 16. Okay, and the factors or the divisors, right, might be a better term here. Factors of 17 is prime, so we only have 1 in 17. So the only common factor here, common divisor, maybe we want to say, so it's more clear, is 1. But this is going to be really tedious once we get up to bigger numbers. So the Euclidean algorithm allows us to streamline this process and just find that GCD after a few sweeps. So I'm going to start with my bigger integer input, 17. 16, the smaller one, is going to be my divisor. Okay, 16 is my divisor. So now 16 goes into 17 once with a remainder of 1. Okay, so this one's kind of boring, right? It's only got one swoop. But like I tried to emphasize here, put it here, in this process, divisor becomes dividend, remainder becomes divisor, okay? Just keep repeating this to yourself every time you swoop through, and that'll help you remember this process, okay? Divisor becomes dividend. So let's see what we're saying here. And in order to understand that reminder, you have to understand each piece. So what we've written here, the division algorithm, we have dividend, so that's what's being divided into. So in this case it's 17 is equal to our divisor, which in this case is 16, times our quotient, which is 1, and plus remainder. And sometimes they call that residue, but in this course we're just going to say remainder. So if we follow along with this hint that we're going to say to ourselves in the middle of the night and keep reminding ourselves over and over again, we're going to make divisor become dividend. So divisor becomes dividend. So this will be 16. Okay, and let's do another color here. And remainder becomes divisor. So our remainder is 1. That's going to become our divisor, 1. Okay, and then we complete the process, right? Because there's a unique quotient, unique remainder based off of just those two things there. So now I'm going to finish this process. Times, okay, 1 goes into 16 times. We have none left over. Once we hit a 0 remainder, this is our stopping point. Okay, once we hit that 0. So once we hit that 0, we're going to look at the previous remainder, and that will be our GCD. Okay, now this extended Euclidean algorithm is going to look really goofy because we only really have one step to work with. If you imagine, and we'll see another example here, we're going to have maybe 5 steps or more steps to combine in order to get that linear combination. In this particular example, our linear combination just smacks us in the face because we've only got one remainder to solve for. So if I look at this equation, 17 equals 16 times 1 plus 1. If I solve for the remainders, which is what I'm going to do with all of these equations that I get after completing the Euclidean algorithm, but in this case there's only one, so it's not that exciting. 17 minus 16. Okay, and notice that's the same exact linear combination that we were talking about before. So no surprise there, but hopefully that gets you a little bit of a direction there with how you want to go about doing this process. And I'll go through and try to find a trickier example here that gives us more steps. The way that we're going to use this process is it's going to allow us to find multiplicative inverses under different moduli. Because if you think about these modular congruences that we've been dealing with, fractions don't live there, right? Like if we think about if we live in, if we live in mod 7, right? So this Z7 contains all possible remainders after being divided by 7. So the only elements that live in there, or at least any integer that I can choose, can be reduced to that form. So any integer that I choose can be written so that it has a remainder from 0 to 6. So so if you think about that, there's no elements that have, like there's no 1/2, right? So if I wanted to solve, for example, if I wanted to solve the congruence, I want to know what integer times 2 is congruent to 3 mod 7. Now that looks really weird, right? Because in our typical equations, our algebraic equations that we're used to working with, we'd say, well, x is equal to 3/2, right? And the way we did that would be by multiplying the multiplicative inverse of this coefficient here, okay? But in Z7, there is no 1/2. So what we're looking for is some element in Z7 that has this property that when I multiply it by 2, I get 1. Okay, so we're looking for a similar type relationship, but we need to realize that, okay, well, 1/2 doesn't really exist here, so what's a corresponding thing? So let's see, 2 times 3 is 6, 2 times 2 is 4, 2 times 4 is 8. Oh, so it's going to be 4. I don't know if you can see that, but let's figure out how to find this multiplicative inverse, okay? And the reason I know it was 4, and you don't have to know this, okay, I'm going to show you a process to find that multiplicative inverse, is I was thinking, okay, I live in Z7, right? So I want to take 2 times something so that I get a remainder of 1. So I'm thinking about multiples of 7 plus 1. So I think like 0 plus 1 is 1, right? But nah, doesn't help us. 7 plus 1 is 8. Oh, I can get to 8, right? Because I know that 8 is congruent to 1 mod 7. That will allow us to end up with just x here on the left-hand side because 8 is congruent to 1 mod 7. So I can substitute in that congruence. So yeah, let's look at how to find the inverse of 2 mod 7. Okay, the multiplicative inverse. The additive inverse is not as exciting. Multiplicative inverse of 2 mod 7. So what we're going to do here is we're going to use the Euclidean algorithm and the extended Euclidean algorithm. And that's going to give us that linear combination, okay? And we're going to look at that linear combination, and that will give us that inverse. And we'll see here in this process, and we'll discuss where that comes from. But at least on this problem, we're going in knowing it should be 4, okay? All right, so with the Euclidean algorithm, what we're looking for is the GCD of 2 and 7. So I'm going to start with the largest input, and the smaller input is going to become my divisor. 2 goes in there 3 times plus a remainder of 1. Okay. Okay, I was worried, but now I'm not worried again anymore. Okay, so divisor becomes dividend, remainder becomes divisor, and we've got a 0 remainder there. Okay, so again, this one's not very exciting. I got a remainder of 1 right away, and on my second step I got 0, so this is really boring. I'll do a more exciting example here next. But if I solve this for 1, actually I'll have my inverse. Okay, it looks different. It's not 4, and that's why I had a little moment. But I forgot I'm going to have a negative value here, so then it's all good. Okay, so if I solve this for 1, which is my remainder, and it's that GCD that I'm trying to get as a linear combination, I'll have 7 minus 2 times 3. And remember, we're interested in that coefficient of 2. So I'm just going to use the commutative property of multiplication here and write this as plus negative 3 times 2. Okay, now this is a step that sometimes throws people off, so stay with me, and I hope this makes sense. Okay, this equation here just lives in our real number world, right? I want to make it live in mod 7 so I can apply this information. Okay, so what I'm going to do is look at each of these pieces and consider what they're congruent to mod 7. Okay, so I know 1 is congruent to 1 mod 7. Okay, and I know that 7 is congruent to 0 mod 7, and I know that negative 3 times 2 is congruent to negative, well, let's leave it, is congruent to, I can just leave it as this if I want to, mod 7. Okay, so basically I'm just going to take this equation and look at it under the mod 7 world. So I'm going to get 1 is congruent to 0 plus negative 3 times 2 mod 7. Okay, so this tells me 1 is congruent to negative 3 times 2 mod 7. It's always good to check your work, right? Is this actually a true congruence? So let's just check here. So notice negative 3 times 2 is negative 6. So if I want to consider make sure that negative 6 is congruent to 1 mod 7. So negative 6 is equal to, let's see, 7 times negative 1 plus 1, right? So yeah, it's congruent to 1. So negative 6 is congruent to 1 mod 7. Okay, and so that tells me that negative 3 is the multiplicative inverse, is we should say right? Because anything congruent to negative 3 mod 7 will work. Inverse of 2 mod 7. Okay, so notice negative 3 is congruent to 4 mod 7, right? Just like I was saying, that's why I had a moment. I was like, oh no, this is not good, right? So it's congruent to 4. So it doesn't matter when you're solving this. You can use negative 3 or 4, but if you say the multiplicative inverse in Z7, then you should have an element in Z7 that's your multiplicative inverse. But that might not always happen. So yeah, just look at this linear combination. Okay, so now let's use this multiplicative inverse to solve this equation here. Okay, so we are trying to solve what number times 2 is equal to, is congruent, congruent to 3 mod 7. Okay, and we just found out that negative 3 is a multiplicative inverse. Okay, so negative 3 is a multiplicative inverse, or I can use 4, right, of 2 mod 7. Okay, so what I'm going to do is take that multiplicative inverse and multiply it by both sides by -3. And I'm going to show you with 4 too, just to be sure that you believe me that it doesn't matter, that there is more than one. You know, it's not unique unless you confine it down to that particular mod, or that particular set, Z7. So I can always multiply both sides of a modular congruence. However, I can't divide, right? Dividing messes us up, as we saw in a previous lecture. Okay. So let's see, let's just do this arithmetic here. And we already know that I'm just going to end up with x here, but I'm going to go ahead and do this multiplication just to demonstrate one more time that that's what happens. Okay, so -9 mod 7. Okay. Now I know -6 mod 7 is 1. We talked about that. I know -9 mod 7 is, let's see, -9 is equal to 7 times -2 plus 5. Does that make sense? I think so. Yeah. It's congruent to 5 mod 7, -14.5. Okay. And then we have it. We've got a solution. X is congruent to 5 mod 7. Let's check our work. Okay, check. So let's plug in 5 for x and see if this works. Notice 2 times 5 is equal to 10. So what the question that we're asking is 10 congruent to 3 mod 7? So 2 times 5. So we want to know, is this a valid congruence? And this is 10. And 10, right? If I write 10, 10 is equal to 7 times 1 plus 3. Yes, we have found the correct solution. Okay, so yeah, so x is congruent to 5 mod 7. So this means for x, I could have any of these integers. So I can add any multiple of 7 to 5, and it'll satisfy this congruence. Okay, let's do 4 just to triple check here. And I think in the next video I'll do a more complicated example of the extended Euclidean algorithm. So now let's say, well, let's test 4 is the multiplicative inverse that lives in Z5, right? Or Z7, sorry. Multiplicative inverse in Z7. Okay, so I'll say I'm going to solve this using 4. So just like last time, I'm going to multiply both sides by 4, see what happens. Hopefully I get the same thing, otherwise I'm in trouble. This is good to check, triple check. 8x is congruent to 12 mod 7. 8 is congruent to 1, definitely, right? 8 is equal to 7 times 1 plus 1. Our remainder is 1, so 8 mod 7 is 1. 12 mod 7 is 5, because 12 is equal to 7 times 1 plus 5. And boom, we get the same solution. All right? Okay, so hopefully that motivates the extended Euclidean algorithm a little bit. I did post some interesting applications of this number theory material. I think I posted some in, let's see, optional but interesting. So yeah, I think there's some interesting applications, especially in cryptography, of these modular congruences and understanding how they work. So keep that in mind, that there are some interesting applications, and check them out if you're interested. So let me know if you have questions or if I messed up somewhere. I'm happy to help. Again, in the next video, I'm going to be doing a more complicated application of the extended Euclidean algorithm, and then I think I will go into developing that Excel spreadsheet to complete this process. Just to kind of automate our process, because when we get to the Chinese remainder theorem, we're going to be having to calculate quite a few inverses. So well, depending on how many congruences there are, so we're going to want a way to do this a little bit more quickly, but I also want you to know how to do it by hand like this, okay? See you soon.